Yeah. So I think that's fine. Uh, yeah. Okay. Great. Okay. Good. So let's start our class. We learned quite a lot in the pulse propagation, right? So one thing, just for a quick review, if we have a pulse, that's what we learned. If we have pulse, we discretize it. And so m equal to 0, right? The first one, m2 equal to 0, corresponding to the maximum peak, right? Center peak. So when you write it, when you include it in the code, in your MATLAB code, so m equal to 0 is the maximum. Then 1, 2, 3, right? 1, 2, 3. Then on the over there, m equal to n, right? Is the corresponding the same point, and then n minus 1 is the lower, right? So let me actually show you the correspondence, right? So this center peak is the piece here. The one on the right, right? The first one on the right is right here, right? And then the second one is right here. But the one on the left, this point, let me use the right shoulder, right? So the left shoulder, this point, the green is this n equal to 1, right? And then the next one is right here. And this piece, m equal to n, that's the point. That's the point for the next period, right? For the next period. It is the same as m equal to 0. So that's how you make the arrangement. Okay, so let's actually, today we will give an example. Just look at the Gaussian pulse propagation. But before that, let's actually go back the how we did the discretized Fourier transform, right? It is natural that it is natural to set. Let's come back, see how this discretized Fourier transform works, right? So let's take a look. The t equals m delta t, right? So Tm, if m is 0, the first point, that means it is t is 0. M is 1, that's the m is 1, this is delta t. M is 2, 2 delta t, right? 2 delta t. Okay, then how much is the delta t? It is m t over n, right? N is total point, n is total point, and then we will divide by the whole time period by n. Okay, omega is n delta omega, right? So m is the index in time domain, n is the index in frequency domain. And then delta omega t, so this is n 2 pi f, the frequency, right? Delta f is 1 over t. So delta f is 1 over t, and so delta omega is 2 pi 1 over t, 2 pi 1 over t. Okay. Remember that our delta omega, what is delta omega? Delta omega is 2 pi over t, right? 2 pi over t. Okay. The full frequency domain, the full frequency domain is n, right? So this is n times delta omega, right? So it is n times delta omega. So that's the total, total we quantify as capital omega. That's the n, capital N times omega, right? So let's say this is the total omega. That is, let me see. So this is the total n times delta omega. So n times delta omega. How much is the n? N is, then we got 2 times total omega. Let me see. So we have the total, the full frequency domain is n times delta omega, right? Because that's the n times delta omega. So this is the total number. This is the frequency grid. So that is capital N times omega. It is capital N times 2 pi over t, right? Capital N times 2 pi over t. So that will give us the t over n, right? So since delta t is t over n, delta t is t over n, so we can also write as the 2 pi over delta t, right? 2 pi over delta t. So 2 pi. Okay, so this is the total omega. That's the total frequency span. This is total time span, right? Just make sure. Okay, so we also want to write exponential I omega t, right? So we want to write this t, this omega, all in the expression of discretized Fourier transform. So discretized domain. What is omega? So it's exponential. I is I. What is the omega? Omega is 2n times 2 pi over t. I omega, right? This is omega. T, what is t? T is m capital T over capital N. There is a, right? It's not continuous moving there. So this equation up to here. Okay, so we can rewrite exponential 2 pi I m and n over capital N. T and T cancel out, right? T and T cancel out. Okay, and T and T cancel out. That's so it's 2 pi I m n over n. Let's dropping z dependent. Dropping z dependent. In u z t and u hat z omega, right? The reason is that what we care about is for the discretized Fourier transform. What we care about is the discretized Fourier transform. So when we take the Fourier transform, we only take the Fourier transform at one specific z, right? So for z here, there's no it's a constant for the Fourier transform, so we can just drop it out. And so what we have is the Fourier transform u omega, right? So it's u hat omega is negative infinity infinity dt ut exponential I omega t. That's the Fourier transform, right? U hat omega is the dt ut exponential I omega t. So let's write it down. What is the, so now it is the discretized, right? Discretized. So how much is ut? Ut become delta t. And then we will actually discretize it, right? So we will discretize it. We said negative infinity to infinity is actually one period, right? One period. So we should be m from 0 to m from 0 to n minus 1, m from 0 to n minus 1, right? So that's the integral. And dt is a constant. We already moved out. What is ut? Ut is represented by am, right? So here is the am, right? So it's am. So we use the discretized am as with subscript m. What is exponential I omega t? Exponential I omega t is right here. It's the exponential 2 pi I m n m little n divided by capital N. Right. Okay. So this is the writing of u hat omega in the form of discretized form, right? Let's assume, let's make the right hand side as the delta t a n hat. Let's make a delta t on the right hand side. The whole sum is the a hat, and with subscript n, right? With subscript n. Okay. So now we have, at least we can write an hat is sum m equal to 0 to capital M, right? Then am exponential 2 pi I m n over capital N, right? So, okay. Can you all see this? Right, let me read it. So a hat n subscript n equals a sum m from 0 to n, am exponential 2 pi I m n over capital N, right? M n over capital N. So in other words, when you take this discretized Fourier transform, first you pick n equal to 0, right? N equal to 0. You integrate from m equal to 0, 1, 2, 3 up to n minus 1. Oh, up to n minus 1. And then you have am exponential 2 pi I m n over n, right? So this is the discretized Fourier transform, right? Any questions so far? Okay, so now let's write the what is a hat, right? Remember, let me keep this equation, right? Because I'm going to write it down again. Going to use it. So now remember this a n hat, right? How much is the a n hat? So a n hat, remember u and am is the direct correspondence, right? So in time domain, am is directly equal to this ut. But now we have an hat is different, right? So this an hat and u hat omega has a correspondence of delta t, right? So this is 1 over delta t u hat omega, right? U hat omega. So this an and u omega has a direct correspondence with a factor of delta t. Okay, so that is n over t, right? N over t. So delta t is t divided by n, right? Delta t is t divided by n. So that then we have this. How much is the omega? U omega, right? How much is the U omega? Okay. So in the U omega, the what we have is also U n delta omega, right? So this is n divided by n over 2 minus 1 greater than 0. In the AN, it is the same thing. When we have the zero frequency, is when n is 0, it's the zero frequency, right? When n is 0, we just simply add AM all together. So in the signal systems, we learn that this is zero frequency, right? So this is the zero frequency. We add together at this piece from 0 for n. For example, we have, if n is 100, right? If n is 100, 100 divided by 2 is 50. 50 minus 1 is 49. So from 0 to 49 is the U n omega. It's the that's the U hat. So that's the U hat, right? So the positive for this half, it is the same as U n omega, but the rest of the half is actually shifted, right? So when n is greater than equal to n over 2 and less than equal to, this is n, right? This is n. This is n, and then we have n minus 1, right? N minus 1. So that's what we have is U hat. U hat. Then we have is n minus n delta omega. Yeah, so this is the delta omega. So n minus capital N delta omega, right? So let's have an example. If my example, so n is 100, right? N is 100. So we get what we have is n is 100. We have the number is from 0, 1, 2, all the way down to 99. All the way down to 99. So for the this is n omega. This is a omega, right? So a omega. So let's look at this, right? A omega. So that would be the 0, right? The 1, 2. So this is 1 and 2, 1, 2. But now when the n is 99, right? When n is 99, when n is 99, let's n 99 minus 100 is negative 1. So this point corresponding to n is 99. That's why we use this equation. Yeah, that's why we use this equation. Yeah, okay. So we'll actually stop here for a while. Let me get a cup of water. So let's pause this. Let's wait for 1 minute. Let me get a cup of water. Okay. Okay. So this is 99, this is 98, right? 98 minus 100 is 2, so it's negative 2. But in the MATLAB or discretized, there is no negative. So basically, it's the same thing. It is going up here. This is 100. It's 99, right? But the whole span, what we're looking at is the 0 to 99. And we learn from the we learn from the signal systems as the Fourier transform actually is a periodic signal. It is the periodic signal. So we have periodic signal in the time domain. We also have periodic signal in the frequency domain, right? And also we have the Gaussian pulse in the time domain will also lead to the Gaussian pulse in the frequency domain, right? Okay, that's this piece. Okay, let's say where delta omega, what is delta omega? Where delta omega is 2 pi over capital T, right? Where delta omega is 2 pi over delta T. Okay. That's this piece. Give me some space. Give me some space. Okay, now next, this is the inverse. This is the Fourier transform, right? Discretize the Fourier transform. Remember, our AM is the same as the U, right? So UT and AM, they are the same, right? And but the U AM hat and U omega has a has a ratio of delta T. Yeah, but it is usually we usually look at the time domain. At the frequency domain, we usually only look at the shape, right? Only look at shape. So with whether we have a delta T or not, it's okay. Right? So now let's take an inverse Fourier transform. UT, what is UT? Is 2 pi. 1 over 2 pi integral from negative infinity infinity d omega u hat omega exponential negative I omega t. Right? Exponential I negative I omega t. Okay. So d omega is delta omega, right? It's delta omega over 2 pi. And then we take a sum. We take a sum. How much is the u hat? Or u hat is this, right? So it's the delta t times a hat. Delta t times a n hat. So it is n from 0 to capital N minus 1. N from 0 to capital N minus 1. Okay, then what we have is the exponential, right? So we have this exponential 2 pi I, right? We learned the exponential is this 2 pi I m n over capital N, right? So um is delta t a n hat. Delta omega, exponential I omega t, exponential this bunch. Right? So now we can write the inverse Fourier transform, right? We can write inverse Fourier transform. So the whole piece is UA, right? The whole piece is UA. So we can further write it down. How much is the delta omega, right? So delta omega is the 2 pi over capital T, right? Delta omega is delta F. What is delta F? Is 1 over T. So 1 over 2 pi, let me copy it down. And then how much is delta t. Delta t is a constant, right? Delta t is constant. Then it's capital T over n, right? Capital T over n. And then we got m from 0 to capital N minus 1. And then we copy an hat exponential 2 pi I mn over n, right? Okay, 2 pi I mn over n. And this whole thing should be am because it is ut, right? This whole thing should be am, right? This whole thing should be am. And let me rewrite it, make it clean, right? Let me rewrite it and make it clean, but t and t cancel out. T and t cancel out, 2 pi and 2 pi cancel out. And we left with 1 over n, right? We left with 1 over n. So let me write it. Okay. So what we have is am is bracket u. Let me write this. Sorry. So let me copy it again first. 1 over capital N into sum n from 0 to capital N minus 1, an hat exponential negative 2 pi I mn over capital N, right? Negative 2 pi I mn over capital N. Okay. Okay, so that is am. That is am, right? This is am, and we can further write it down. What is am? What is am? Is the bracket curly bracket? Then we have u z, not z. I shouldn't include the z here, right? So what is u m delta t when m is less than n over 2 minus 1 greater than equal to 0. So for the case of n is 100, it's 0 to 49, 0 to 49, right? So this piece is 0 to up to here is 49. Then we have 50 up to 99, right? So m is less than equal to n minus 1, greater than equal to n over 2. It's 50 minus 40, 50 up to 49, right? 50 up to 49. So that is u m minus capital N times delta t, right? M minus n times delta t, right? Okay, so we have half of it on the right shoulder. It's 0 to 49, and another half is 50 to 99 is on the other shoulder, right? But those two shoulders actually not symmetric. They're not symmetric. So there's one thing, there's one on the center. The pick one is at m equal to 0, right? Pick one is at m equal to 0. So those are not symmetric. Those are not symmetric. So all the signal in time domain and in frequency domain needs to be shifted. All the time domain and frequency domain, they need to be shifted, right? So I'll deal with. I'll let you know this. I'll let you know how we should do shift later on. But for now, we have where delta t is capital T over n, right? And then where that the Fourier transform, the Fourier transform must be appropriately shifted. Right? The Fourier transform must be appropriately shifted. So that needs to be appropriately shifted. And also some package like MATLAB, which we will be using for our class. Some packages like MATLAB. Some packages like MATLAB use 1 to n, right? We'll use 1. They don't have the index 0, so it's 1 to n, not 0 to n minus 1. You know, so in this case, we'll just make sure A1 is U0, right? A2 is U1, U delta t. Just be careful. Now my A1, that means the centerpiece, the first index is U0, which is the center maximum in the Gaussian pulse. A2 is U delta t, is this the first one on the right. The first one on the right. Okay. Okay. Any questions so far? So now we went through the discretized Fourier transform. I want to let you know this is how it is done, right? So in the discretized Fourier transform, we have AM, right? So in the once we have that, this is given. AM is given. It's the Gaussian pulse here. In order to get discretized Fourier transform, with AM times exponential I 2 pi I mn, right? M is 0, M is 0, A0, so you just put 0. So A0 is actually sum of this AN, just sum of this. So it's just the average. And A1 is that 2 pi I, so it's M going to be from 0 to n minus 1. N is always 1. So you take a Fourier transform. And then you can take an inverse Fourier transform, right? Inverse Fourier transform. Be aware, the AN is the signal in AM is the signal in time domain, but AN hat is the signal in frequency domain has a ratio of delta t, right? Has a ratio of delta t because it is a constant. It is a constant. We don't, in the spectral domain, we only need to have the shape, right? We only need to have the shape. But keep in mind, AN hat and U omega has a ratio of delta t. But it is okay because delta t is a constant. Okay. And questions so far? Okay, so we did. Well, we actually we don't need it. We don't need it. So now let's see what we learned. Right? We have U0T. We want to have U0 omega, and then we want to learn that UZ omega. Right? And then this is hat. And then we come back at UZT. Right? What we learn is that we need to take a Fourier transform, right? This piece, Fourier transform. Then we need to propagate the signal. How should we propagate? We just multiply exponential I k naught double prime omega, right? Remember, so it's just simply multiply a phase term, right? Exponential. And then the last one, right? The last one is the inverse Fourier transform. So that's the complete, is the pulse propagation, right? Anything pulse propagation, this could be in optical fiber. This could be in a, in a wire, any wire or any waveguide, any waveguide, any wire. It's a general, right? It's a general concept. So let's start now. Let's start with a very simple and straightforward. Well, it's relatively straightforward. Let's put it this way. Relatively straightforward Gaussian pulse. So if I have a Gaussian pulse here, what happened on the frequency Fourier transform propagation, and then come back to the inverse Fourier transform. If I have a Gaussian pulse, what kind of shape it is here, right? So let's have a demo, right? Demo dispersion of a Gaussian pulse. Demo dispersion of a Gaussian pulse, right? And this problem can be done analytically. This problem can be done analytically, right? This problem can be done analytically. So we will do it analytically, and then I think we have the example to do it numerically, as we explained previously, and see whether they actually agree, right? Okay, so we have the pulse, right? So we have the pulse. We write Gaussian pulse. Gaussian pulse, right? So we have U ZT, right? Yeah, and ZT is a exponential negative t squared over 2t naught squared, right? So it is a exponential negative t squared over 2t naught squared. So this is the pulse. Let's look at the power or intensity, right? So it's now U0t, right? U0t. Let's take absolute value square, right? Absolute value square. So it's a square exponential. Take a square. It is basically a factor of 2. So it is negative t square over t naught square, right? T square over t naught square. And then we have, so T naught basically specify the width. T naught basically specify the width, right? So let's take a look. So the pulse is usually determined by its so-called 4-wave half maximum. So we have pulse here, right, in time domain. So this is the maximum. So this is the half, right? So it's called T. It's called T, 4-wave half maximum, right? So it's the 4-wave half maximum. It's 4-wave half maximum. 4-wave half maximum. So that's why the abbreviation would FWHM, right? So we have the 4 waves, but half maximum, right? So this is a way to quantify the width of the pulse, right? Whether the width is relatively fat or the width is relatively short, right? Slim. Okay, so now we put it into this T, right? Let's put it into this T. So now we have U0 and T, 4 with half maximum over 2, right? So this is 4-wave half maximum, and this point is T 4-wave half maximum over 2. At this point, the power should be the half of the peak power, right? So this power should be this at the, it should be A squared over 2, right? Should be A, the peak, divided by 2, right? Peak divided by 2. How much is this value? And this value should be A squared exponential negative T 4-wave half maximum over 2 square divided by T naught square. Right? Divide by T naught square. So I just substitute T by T 4-wave half maximum, divide by 2, and then divide by T naught square. Divide by T naught square. Okay? Okay.
Dr. Hu,
Questions?
I have a question on the first line, the Gaussian pulse. Is that a 2 in the denominator?
Yes.
Where does that go?
There is a 2 in the denominator. The reason we have a 2 is to remove it after the power. So once we have the power, this 2 is gone.
Okay.
Then we can relate it T naught directly back with this T 4-wave half maximum. So it's the, we leave this T on purpose.
Okay, thank you.
Sure. Okay, great. Yeah, so you take a square, the T2 is gone. Okay, right. So this A and A cancel out. This A and A cancel out. Yeah, thanks for asking. A and A cancel out. So take a natural log, right? A and A take out natural log. So this whole piece is negative T 4-wave half maximum over 2 square over T naught square, right? It is the, so this piece A square cancel out, it's half. Let's take a natural log, right? Natural log. So that's this piece. So what we have is we want to have a relationship with T naught and 4-wave half maximum, right? So I move T naught on the right hand side. So T naught equals then we take a square root, right? So it's the T 4-wave half maximum divided, excuse me, divided by, excuse me, 2 natural log, it's 2, and then square root, right? So T naught is T 4-wave half maximum divided by 2 because there's a 2, right? And then we move the natural log half to the left-hand side. And it should be natural log of half because of the negative sign, so flip. So it's natural log of 2, but square root, right? Because originally we have square here. So we have the direct relationship between T naught and the T 4-wave half maximum, right? So let's calculate. This is just a constant. This piece is just a constant. It's usually approximately T 4-wave half maximum divided by 1.665, and it is about 0.6006 T 4-wave half maximum. Right? Okay. Okay. So now for a pulse width, for a pulse width T for a pulse width T 4-wave half maximum is 20 picosecond. So it's quite small, right? Picosecond. So you think it's nanosecond and then below nanosecond. Picosecond is the 1/1000th of nanosecond. So it's quite small, right? So T before we have maximum is 20 picosecond. How much is the T, right? T naught is going to be 20 picosecond times 0.606, which is approximately 12 picosecond. 12 picosecond. So when we know experimentally, therefore we have maximum in power, right? This is the in power is 20 picosecond. Then we can directly state that T naught is approximately 12 picosecond, 12 picosecond. Then this pulse will represent a 4-wave half maximum of 20 picosecond in power, right? When we say 4-wave half maximum, we're always referring to the intensity and power. Good? Yeah. So this is a Gaussian pulse. Okay, questions? Okay, so now let's look at the first leg, right? So we have the we have this Fourier transform. So we will do a dispersion of. Let me use this also. So this will be the first leg, right? So this will be first leg, right? First leg, what we're going to do is 0t Fourier transform to u0 omega, right? This is hat. And the u0 omega hat is the Fourier transform A negative frequency, negative infinity to positive infinity, dt exponential, right? It was originally ut. What is ut? It's the exponential negative t naught over 2t naught square. It's actually not t naught. T square over 2t naught square. And the exponential I omega t. And exponential I omega t.
Excuse me, Dr. Who?
Yes.
What is that an H front?
Oh, you mean here?
Yeah.
As a.
Oh, okay.
Amplitude.
Gotcha. Okay.
Yeah.
That makes more sense. Thanks.
Yeah. Thank you. Thanks for asking. I actually prefer more interactive. Interactive. So A negative infinity to infinity dt. This is just dt. This is u, right? This is u. U actually is A this, right? Having 2, as you asked, once it's squared, the 2 is gone, right? Exponential I omega t. So the Fourier transform. Okay, so this Fourier transform, this integral is not straightforward. This integral is not straightforward. However, there is a table. There is a table for the Fourier transform. So we'll just, overall, we're not math class, right? We're engineering class. So we have a table. Use negative infinity, exponential negative ax squared minus bx dx equals square root of x over a exponential b over 4a, b squared over 4a, right? So we'll use this table, right? We can get that. Okay, so in this case, there's T, B, how much is the B here? B is I omega, right? B is I omega. How much is the, B actually is negative I omega, right? B is negative I omega. How much is the A? A is T, right? AS is 1 over 2t squared, 2t naught squared, right? One is A is exponential 2t squared, right? A is exponential 1 over 2t naught squared. Okay, so we take this, right? Take that. What we have is the and then we got exponential, right? So we have square root, right? So square root of x. No, sorry, this is not x. This is pi. This is pi. This is pi, right? This is pi. So this will be pi. How much is the A? A is 2t naught squared. A is 2t naught squared, right? And then exponential, how much is the A? It's 4 times 2t naught squared. How much is the B? B is I omega, right? B is I omega. So negative omega squared, right? And then this is the A, right? So A is well 2t naught. So 2t naught is on the numerator, right? Because it's 1 over A. It's 1 over A, 1 over A. So it's 2t naught squared. Okay. Okay. Are we good? Right? Okay. So that's the 2t naught squared. So the result is square root of 2 pi t naught exponential. This is 2, right? Negative omega square t naught square, right? That is the Fourier transform of the this Gaussian pulse, and you can see it's omega dependent, and the shape of this function is also Gaussian, right? The shape of this function is also Gaussian. It's a Gaussian shape. Okay, that's good. Let's also do the 4-wave half maximum, right? Let's also do the take the bandwidth. This bandwidth, right? Bandwidth. Let's look at also 4-wave half maximum of this this bandwidth, right? So let's take a U0 and U0, 4-wave half maximum, 4-wave half maximum of 2, right? Of 2 is this U0, 4-wave half maximum square root, right? Square root should be the half of U0 and 0, right? So this is the center, it's a Gaussian pulse, so it's half, right? Half of the peak power. So at the 4-wave half maximum, right? So this is time domain, you will plot a frequency domain, whatever shape, right? So this is also omega 4-wave half maximum, but at this omega 4-wave half maximum over 2, this is the half, right, in power. What it means is that I take an absolute value, so it's an exponential, right? Exponential, take a square, negative 4-wave half maximum over 2 square t naught square. This should be half, right? I only look at half of it. I only look at half of it. I only look at exponential omega dependent, right? This is a constant. I don't need to, put into the calculation. It's just the amplitude. So this piece, I take a square. So this factor of 2 is gone, right? Take a square, factor of 2 is gone. But omega 4 half maximum over 2 square is half, right? Omega half is half. Okay, so it's almost the similar equation. My 4-wave half maximum. So it's the omega 4-wave half maximum. No. Yeah. Omega 4-wave half maximum equals, right? So we take a nature log, and then we move the T naught to the right hand side, take a square root and put the factor of 2 on the right hand side. So this is the 2 nature log 2, right? It was nature log half, but since there's a negative sign, so we flipped, become nature log 2, and we still need to have the square root. We still need to have the square root over T naught, right? Over T naught. Again, this number is about 1.665 over T naught, right? Or 1.665 over T naught. And if we calculate it, if we calculate T naught as, remember how much is the T naught if we have 4-wave half maximum 20 picosecond? 12, right? 12 picosecond. So let's calculate it. It's the 12 picosecond, it's 1.665. And since it's 12 picoseconds, 0.012 nanosecond, right? Nanosecond, which is the total. If we calculate, it's 1.665 over 0.02, and this is the gigahertz, right? So that's the amount. That's the amount of this by some gigahertz, right? So the bandwidth is about 200 gigahertz. This bandwidth is about 200 gigahertz, right? So that's the calculation. That's the calculation. Okay, so this is the 4-wave half maximum. This is the omega in angular frequency. How about frequency? It is the omega 4-wave half maximum divided by 2 pi, and that is the you can directly calculate, right? I'm not going to write it down because I don't have space. So I have some space there. So this would be 1.665 over 2 pi times 0.012 gigahertz, right? But this is angular frequency, right? This is the angular frequency. So this is the frequency, right? Okay. So that's those are the first leg. Questions on the first leg? Okay. So if we're okay, let's look at the second leg, right? So what we have is, it is still a Gaussian pulse. The 4-wave half maximum is 1.665 over T naught. So what we learn here is that if I have a T naught, if I have a relatively wide pulse, then after Fourier transform, the frequency is a bit narrow, But if I have a relatively narrow pulse, then this is small, then the frequency domain, it is a wide spectrum, right? That's what we learned from the signal and systems class. If in the Fourier transform, if the pulse is wide, then frequency is small, and the pulse is narrow, frequency is wide. Right? Okay. Okay. Yeah. With that, we can look at the second leg, right? I think we have time at least finish the second leg. So this is the second leg. Sorry, I remove it. I should have, no. Right? So this is the second leg, right? Second leg is U hat 0 omega. We propagate to Z omega, right? We propagate. So now we learn that Z omega hat and U 0 omega hat, right? So this is actually the propagation. This is propagation at 0 and now propagate to Z, right? So this is the second leg here. Second leg here. And what happened is exponential I k naught double prime over 2 omega square Z. Right? So this is what we derived maybe last week, Monday also, right? We spent some time, we derive it, right? Now we're going to use it. And we actually, there is more terms, right? K naught triple prime, K naught fourth prime, fifth prime. But now we're looking at most fundamental term. That's the dispersion. That's the dispersion. And we will think about high order term also. We will think about high order term also. So normally we measure, dispersion. We normally measure dispersion D in units of picosecond per nanometer kilometer. So we kilometer. We measure the units of picosecond per nanometer per kilometer. Why? So here's the dispersion, right? What is dispersion? Dispersion is due to the different frequency propagating at different speed. Different frequency propagating at different speed. So after a section of fiber, it propagates, become a wider pulse, right? Because some of the frequency propagate slow, some of the frequency propagate fast, right? So we want to see how to quantify this dispersion is that this is in time domain, in frequency domain, right? We have this, originally it's the frequency domain, we actually become some shape, right? But what is the speed difference between this point and this point? Omega 1 and omega 2. Right? Or lambda 1, lambda 2. So per wavelength, per nanometer, well, if we have per nanometer and we propagate 1 kilometer, what is the speed of those two cause any difference of the arrival time, right? So the arrival time is picosecond. So once this point and this point, at what time they arrive? What's the difference in time between lambda 1 and lambda 2? What's the difference in between lambda 1 and lambda 2 in nanometer width? What is the time difference? And if we propagate per unit length, of course we say per kilometer. So if we propagate per kilometer, how much time we elapse the difference per delta wavelength, right? That's why we have this unit, picosecond per nanometer per kilometer. Of course, we got propagate 1 kilometer, we got this. We propagate 2 kilometer, and this value needs to be added up, right? Needs to be added up. Now we have this, and so D is, so now when I have D is D K naught prime D lambda, right? K naught prime D lambda. Remember, what is K naught prime? It's 1 over group velocity, right? What is the, right? 1 over velocity. So if we look at the unit, right? This unit, D is 1 over group velocity. Group velocity is meter over second, right? D lambda is times the meter, right? The meter. So overall, it is the second over meter times meter. So the unit for this D K naught prime, D K naught, what is the D K naught prime? K naught prime is 1 over group velocity, right? How much is the propagate, right? So over D lambda. So K naught prime has the unit of 1 over Vg. Vg is meter per second times D lambda is meter. So it is second over meter. So this is consistent with picosecond nanometer per kilometer. However, we just usually we quantify this D by picosecond nanometer kilometer. All right. Okay. Let's finish this K naught double prime, and then we're done today, right? So noting K naught double prime as K naught prime d omega, right? Remember we did the Fourier transform. So K naught prime, and then take another derivative is K naught double prime, and then what we have is d omega d K naught prime, right? And then we add a d lambda there. We just add a d lambda, right? D lambda d omega, right? Now let's say, let me write it down directly. So what is this piece? This piece is d, right? And d lambda over d omega is negative 2 pi c over omega square, omega naught square, right? And then what is the why it is the case? It is because omega naught over c equal to 2 pi over lambda naught, right? So this is the K naught. This is the propagation constant is 2 pi over lambda naught. It is omega naught over c. So lambda naught is 2 pi c over omega naught, right? Lambda naught is 2 pi c. Lambda naught move to the left-hand side is 2 pi c over omega naught. And the d lambda, right, is negative 2 pi c over omega naught square, right? Take a derivative, d omega, right? So we take a derivative, and then it's 2 pi c, omega naught is negative 1, we have negative 2, right? So it's in the denominator d omega, right? So d lambda over denominator, d lambda over d omega is 2 pi c over omega naught square. Okay, So that's this piece, and we can further write it down. We can further write it down. Omega naught over c is 2 pi over lambda, 2 pi over lambda. So we can further write it down, become negative lambda naught over omega naught square, omega naught, right? So omega naught over c is 2 pi over lambda. So we simplify it, right? Okay, we can further make it omega is 2 pi c over lambda. So we can still write it to negative lambda square 2 pi c, right? D. Okay, we will finish here. We will finish here. So basically, we introduce the dispersion D is D K naught prime over D lambda. But when we take the Fourier transform, when we take the Taylor expansion, what we did is the K naught prime D omega. So we need to convert D omega to D lambda, right? So this piece is capital D is the dispersion. D lambda, D omega, we can use this relationship, wave number relationship. Lambda is this piece, D lambda is 2 pi c over lambda square. And now we can change it to 2 pi c over lambda naught, over omega naught square. And since omega and lambda naught has the relationship, has this relationship, so we can write this form, that form, or totally lambda naught square, right? This is just a way, preferred way of writing, right? Preferred way of writing, okay?